Hello, my name is Oscar, and today we're working on chapter 9 and 10 examination. So our first exercise is about a cylinder rotating in its central axis. So for part A, we need to find the angular speed. So the values that we have right now, first we have mass. For our mass, we have 12 kilograms. We have radius. For our radius, we have 0.250 meters. We have the work done. This is gonna be 75 joules. We have initial angular velocity. And this is going to be 0 radians per second. So like I say, we need to find the final angular speed. So the formulas that we are going to use, we have the work energy theorem, which is going to be work equal to 1.5 I which is momentum, final angular speed to the power of 2 minus the initial angular speed to the power of 2. And the formula for the moment of inertia of a cylinder rotating about its central axis. So the formula is going to be I equal to 1.5 times mass times radius to the power of 2. So to start with this, we're gonna use the first formula for work, which is equal to 1.5, and we're gonna substitute this part I, so it's going to be 1.5 times 1.5 times mass times radius to the power of 2 times final angular velocity to the power of 2. And like we know, the initial angular velocity is 0, so it cancels, it's gonna be 0, so we're gonna leave it alone. So now we multiply this by this by this, and we're gonna have work, it's equal to 1.5 times mass. This is going to be 1/4 times mass times radius to the power of 2 times the final angular velocity to the power of 2. So like we need to find the final angular velocity, we're gonna isolate final angular velocity, and this is going to be equal to final angular velocity equals to the square root of 4 times the work done over mass times radius to the power of 2. Now we need to replace our values. We need to plot our values. So this is going to be equal to, we have 4, this is going to be 75.0 over, our mass is 12 kilograms, and our radius is going to be 0.250 meters to the power of 2. All of this, we're gonna do the square root of all of this. So when we do the operation, we got the square root of 300 over 0.75, and the square root of this is going to be equal, so the final result is going to be 20.0 radians per second. So this right here is going to be our final velocity, final angular velocity. So this is the answer for part A. So now for part B. We need to find the final angular velocity if we had an initial angular velocity of 12 radians. So this is going to be 12 radians, 12.0 radians per second. So we already know the formula, so it's going to be, hold on, okay, let's keep going. So now we already know the formula, so we had work done is equal to 1.5, we replace I, inertia, so it's going to be times 1.5 times mass times radius to the power of 2 times final angular velocity to the power of 2 minus initial angular velocity to the power of 2. So what we're going to do right now is operate this with this, then we're going to move the result to this area and then move this. So as a result, we're going to have when we multiply this by this and then we move this to this area, we're going to have 4 times work done over mass times radius to the power of 2 equal to final angular velocity to the power of 2 minus initial angular velocity to the power of 2. So now we're gonna move this right here, so it's gonna add the part right here, having as result final angular velocity to the power of 2 is equal to initial angular velocity to the power of 2 plus 4 times work done over mass to the times radius to the power of 2. And the next step is going to be the same, but the square root. So we're going to start to plot the numbers. So final angular velocity, it's going to be equal to the square root of our initial angular velocity is going to be 12 radians. So we're going to have 12 to the power of 2 plus 4 times 75.0 over 12 times 0.250 to the power of 2. when we operate, our result is going to be final angular velocity is going to be equal to the square root of 144 plus 400. So now we need to find the square root of 544, which is equal to 23.3 radians per second. So this will be the final angular velocity when our initial angular velocity is equal to 12 radians per second. That's the solution for part B. If we do a sketch of the first exercise, we're gonna have a cylinder right here, and this cylinder is rotating in its central axis. Doing a work of 75 joules. Its mass is equal to 12 kilograms. Its radius it's equal to 0.250, and depending on the part, if it is part A, we don't have an initial velocity, angular velocity, but for part B we have an initial angular velocity of 12 radians per second. Yeah, so that's the diagram for part A and B. And like I said, the only change is for part A, our initial angular velocity is going to be 0, but for part B, which is right here, it's going to be 12 radians per second. So we're going to start with part C, which is another exercise or problem. For part C, we have a square plate that is rotating with no friction around its axis through its center and perpendicular to the plane of the plate. So our mass is going to be equal to 0.600 kilograms. The side length each equal to 0.150 meters. The formula that we are going to use is work done is equal to 1.5 times inertia times final angular velocity to the power of 2 minus initial angular velocity to the power of 2. We're also going to use the formula for a square plate rotating about its center, which is I, or inertia, equals to 1/6 times meters times the side length to the power of 2. So we're going to start. We have work done is equal to 1.5. We're gonna substitute I, or inertia, for these values, for this formula. So we're gonna have 1.5 times 1/6 times mass times side length to the power of 2 times final angular velocity to the power of 2 minus initial angular velocity to the power of 2. So we're gonna start to operate all of this. So we're going to plot the numbers. So we have work done is equal to 1.5 times 1/6 times mass, which is equal to 0.600 times side length, which is equal to 0.150 to the power of 2. The exercise also told us that the final angular velocity was equal to 40. So we have 40 to the power of 2 minus 0 to the power of 2. So this is going to cancel. So now we have the work done is equal to 1/12 times 0.600 times 0.150 to the power of 2 times 40 to the power of 2. When we do the operation, work done, it's going to be equal to 1.80 joules. So this will be the answer for part C. The work done when the final angular velocity is 40 and the initial is 0. So now for part D, we have to do the same thing, but instead of having an initial velocity of 0, our initial velocity right now is going to be 40, and our final angular velocity is going to be 80. So we're going to use this formula right here. So work done, it's equal to 1.5 times 1/6 times mass times side length to the power of 2 times final angular velocity to the power of 2 minus final angular velocity to the power of 2. So now we have 1/2 times 1/6 times 0.600 times the side length was 0.150 to the power of 2. We close the parentheses, we open the new parentheses, and this is going to be the 80.0 to the power of 2 minus 40.0 to the power of 2. So when we do the operation for all these values, or all these values, we got that the work done, it's equal to 5.40 joules. It was the same process, same formula, and yeah, that's the answer for part C and part D, which is the second problem. Our diagram for this for part C and part D will be something like this. We have a square that is rotating, so we have the side length, which is L. That was 0.150 meters. We have our mass, so this is going to be 0.600 kilograms. And yeah, for part C, it went from 0 to 40 radians per second, and for part D, it was 40.0 to 80.0 radians per second. So now for part E, or exercise number 3, this is going to be part E and part F. So we have a cylinder and there is a cable attached to the cylinder, and the cable has a block of cheese. So for part C, we need to find the height from which the block of cheese must fall so that it reaches a speed of 4 meters per second right before hitting the ground. So the values that we have right now is our mass, which is equal to 2 kilograms. We're gonna put a small c right here because this is the mass of the hollow cylinder. The inner radius, so it's a cylinder with 2 different radius, so it's going to be something like this and like this. The inner radius is going to be here, and the outer radius is going to be from here to here. So okay, so the inner radius, it's equal to 0.100 meters. The outer radius, we mark the I and the O so we can see the difference between the radius. So the second radius, or the outer radius, is going to be 0.200 meters. The mass of the CH, which is going to be cheese, is equal to 0.500 kilograms. We have the final velocity, because the exercise is asking us for the final velocity to be 4 meters per second. So 4 meters per second. We also going to use gravity or acceleration, which is going to be 9.8 meters per second to the power of 2. We need to find the height to have this final velocity. So the formulas that we are going to use, we have inertia equals to 1.5 times mass, and we're gonna have the difference of the radius. So it's going to be the inner radius to the power of 2 plus, I mean, it's not a difference, sorry about it, plus the outer radius to the power of 2. We also have energy conservation, so we have the mass of the cylinder times gravity times the height equals to 1.5 mass of the cylinder times velocity to the power of 2 plus 1.5 times inertia times angular velocity to the power of 2. And we also have the velocity is equal to the outer radius over the angular velocity. So right now we're gonna start with the formula of inertia. So we have inertia equals to 1.5. Our mass is 2 kilograms. Times 0.100 to the power of 2 plus 0.200 to the power of 2, which is the inner radius and the outer radius. This operation is going to give us as result the result of 0.05. Now we need to find the angular velocity, so we can use this formula. So we have, if we use this formula right now, we can isolate angular velocity. So we have the angular velocity it's equal to velocity over order values. And this is going to be equal to the 4 meters per second over 2.200 meters, and angular velocity it's going to be equal to 20 radians per second. So now that we have inertia and angular velocity, we're gonna use the formula of energy conservation. So we have our mass. So let's go right here. Mass of the cylinder. Mass of the cylinder times gravity times height times 1.5. I mean equals to 1.5 times mass times mass of the cylinder times velocity to the power of 2 plus 1.5 inertia times the angular velocity to the power of 2. So we have, now we plot the numbers, we have 0.500 times 9.8 times height. This is what we need to find right now. This is equal to 1.5 times 0.500 times the velocity to the power of 2 plus 1.5. We know inertia is 0.5 times 0.5 times the angular velocity, which is 20 radians per second. And right now we're gonna have 4.9 times height equals to 4.0 plus 10. So height is equal. So we're gonna add these two numbers, and like 4.9, it's multiplying height, it's going to divide this value. And the result of 4.0 plus 10.0 divided by 400, I mean 4.9. 4.9, it's going to be equal to 2.86 meters. So that's the height we need for the block of schist to hit a velocity of 4 meters per second before hitting the ground. For part F, it is asking us for the angular velocity of the cylinder just before the schist hit. My bad. Part F is asking us for the angular speed of the cylinder just before the schist hits the ground. So we already found the angular velocity, which is right here, 20 radians per second. So this is the answer for part F. So now for the last exercise of problem, we have part G and part G and part H. We have a pulley with a shape of a cylinder. There is friction and it has a textbook. So for part G, we need to find the speed of the textbook before hitting the floor. So part G, the mass of the pulley, we're gonna mark the mass with P so that we know it's the pulley. It's equal to 1.50 kilograms. We have a radius which is equal to 0.240 meters. We have the mass of the book, so we're gonna mark a little b so we can know that it is the mass of the book, which is 2.0 kilograms. We have the height, which is equal to 0.900 meters. We have the angular velocity, which is equal to 10 radians per second. And we have, so now we're gonna use the energy conservation formula. So we have the energy conservation formula, but we are going to add the friction. So it's going to be the mass of the book times gravity sorry, times the height equals 1.5 times mass of the book times velocity to a power of 2 plus 1.5 times inertia times angular velocity to a power of 2. And now we're gonna add the work by friction, so minus work by friction. We also have the formula for velocity, which is equal to radius times angular velocity. For part G, like we need to find the speed of this book before hitting the floor. We're gonna use this formula right here, which is velocity. Velocity is equal to a radius, which is 2.240 meters, times the angular velocity, which is 10 radians per second. So we have velocity, it's equal to 2.40 meters per second. So that's the answer for part G. And for part H, we're gonna use the formula of energy conservation with friction. So we need to find for part H, we need to find the work done by friction. So we need to isolate work done by friction. So that's going to be we also need to find inertia. So for inertia, let's start with inertia. Inertia, it's going to be equal to 1.5 times mass times the radius to the power of 2. So we have inertia is equal to, let's say, 0.5 times the mass, which is equal to 150 kilograms, because this is the mass of the pulley, times radius, which is equal to 0.240 to the power of 2. When we solve, we have the result of inertia, which is equal to 0.0432. Now we can use this inertia in the energy conservation formula with friction. So we're going to have the mass of the book times gravity times height equals to 1.5 times mass of the book times velocity to the power of 2 plus 1/2 times inertia times angular velocity minus friction. So this is going to be 2 times 9.8 times 0.900 equals to 1.5 times 2 times velocity, which is 2.40 to the power of 2 plus 1.5 times the the angular velocity, which is equal to 10. This is going to be 10 to the power of 2 minus work by friction. When we solve this first part right here, we got 17.64 equals this part right here. It's going to give us the result of 5.76 plus 2.16 minus the work done by friction. So now we need to isolate work done by friction. So we are gonna move this right here. So it's going to be 70.64 minus 5.76 minus 2.16 equals to minus work by friction. The result of this is going to be work by friction. It's equal to -1 times 9.7, and this is going to be equal to 9.7. So how did I find this -1? Because you can see that I have the negative of work by friction, so we can say that we have a -1 right here. Oh my god, this is multiplying, this is going to divide so this will be work done by friction is equal to 9.7 divided by -1. Positive times negative, it's going to be negative. So negative 9.7 joules. So this is the work done by friction and the solution for part H. Thank you so much for your attention.